Okay, this video is just going to be a brief summary of some of the biggest points that we had to make in electrostatic equilibrium. Keep these things in mind always. Some of them are easy to forget, and if you keep these in mind, it will keep you out of trouble most of the time. Now, of course, there are many other points that could be added here, but we'll discuss those as needed in class. So the first major point that needs to be made or reviewed is that the electric field is zero for all points inside of a conductor. And the reason for that is not entirely clear to me, other than the electric fields inside of a conductor are complex, and fields do exist all the way down at the atomic level. However, those fields will always interact in such a way that it creates a net field at all points in space of zero. Now, point number two, excess charge is going to be on the surface of conductors. And this really goes back to our basic fundamental understanding of what it means to charge something, even with last year. And that the only charges which are free to move about are going to be electrons when we're talking about solids. So it's the electrons which move around. So if you have a positively charged object, there's a deficiency of electrons, and the proton fields are coming out of the atoms themselves, and that's what's creating the positive charge of the object. If you have a negative charge, then it's because there's an excess of electrons. And most objects are neutrally charged, or very close to neutrally charged, which means there's about the same number of protons and electrons. At the surface of a conductor, the electric field is always perpendicular to the surface. And this is going to be similar to the gravitational field. When we're standing on the surface of the Earth appears to be flat, and the electric field, the gravitational field appears to point straight down. So this would be G. If you start to zoom out and you get high up into the atmosphere, you'll begin to see that the Earth is actually curved and that the gravitational field is pointing towards the center of the Earth. And so that's the idea behind the electric field always being perpendicular to the surface of a conductor. It's that when you get close enough to that surface, the field is going to be pushed straight because of the charges. Now if I do the electric stuff in white here, you got charges here. And those charges have field lines that are trying to come out radially, but they push themselves straight into alignment. And so the electric field at the surface is going to be perpendicular. In terms of potential, all points on and inside of a metal have the same potential. And the reason all points will have the same potential is because the electric field is equal to zero. And fields lead to work being done. And if no work can be done, then there's no change in potential energy, which means the change in potential is equal to zero. All right, so you will gain or lose potential as you approach the metal, the conductor. But once you get to the surface and once you get inside, the potential remains constant. There's just no possibility for the potential to change because the field is now zero. Positive charges naturally go from high potential to low potential, and negative charges go from low potential to high potential. There's no good gravitational analogy for that, because a positive charge would be the equivalent of mass, and mass always seeks a lower location. So if you drop a rock, you never see it go up. Right? So, but we don't have anything that we drop that actually goes in the wrong direction. They call that levitation, and that doesn't make any sense. So we don't have any good analogies in the world of mass. And then finally, surface charge density. And remember, we used the Greek letter sigma for that. The surface charge density is going to be greatest at sharp corners. So if we look at a shape like this, then what you find is that the charges are going to be on the surface. If this is a conductor, they're going to be pretty spread out here on this large radius of curvature, but down here all those charges are going to be squeezed into a really small area. And so what you end up with is a very large electric field in this region here. It's going to be very large. And out here, the electric field is going to be, much diminished in comparison. This large electric field means that there's also going to be a large potential difference that's going on there. Lightning rods work off of this principle. And so what ends up happening is, a cloud passes overhead. So you got a storm cloud here, and it's all charged up. It's ready to throw a lightning bolt, and you've got your house, and on your house you have a lightning rod, which is right here. And what ends up happening is you create a really strong electric field around the tip of the lightning rod, which comes to a point, and so you end up bleeding off some of the excess charge, and it comes down through the lightning rod into the ground. So the purpose of the lightning rod is actually to avoid a lightning strike, not to cause a lightning strike. However, if a lightning strike does occur, it's going to hit the rod, and it's much safer for the lightning to strike the rod than some other part of your house.